In this problem we have the alpha particle that is attracted to the gold nucleus, and because of the attraction force it will move towards it, but then because of the like charges, the repulsion electric force will stop the alpha particle a certain distance d from the nucleus. And at that point we want to find what initial velocity or kinetic energy will the alpha particle have in order to reach this distance d before it's stopped by the repulsion force. So we can think of this as we have some kinetic energy initial Ki, we have potential energy, initial electric potential energy, but because the distance from the alpha particle initially to the gold nucleus is relatively large compared to the stopping distance, we can approximate this to be 0. And then we have the final kinetic energy, which we're going to call K sub F. We're going to set that equal to 0, otherwise D would be smaller. And then we have some final potential energy given by our electric potential energy formula. And now we can say that from conservation of energy, this must be true, that the sum of the kinetic and potential energies initially has to equal the sum of the kinetic and potential energies finally. And since initial potential energy and final potential energy are 0, then we have the initial kinetic energy has to equal the final potential energy. And the final potential energy is given by K Q1 Q2 over R. If you remember from our 203, K was 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. The first charge is an alpha particle, so it's 2 times 1.6 times 10 to the negative 19 coulombs. The second one is the nucleus of the gold, which has 79 charges of that of the electron. And we're just taking absolute values here. And the stopping distance between them R is going to be our D, which is 5.0 times 10 to the negative 14th meter. And this will give us 7.3 times 10 to the minus 13 joules, which is the same as 4.6 times 10 to the 6th electron volt, or 4.6 mega electron volts.